So this afternoon, let's warm it up with some eMMC, SD, SDIO, and block layer. Actually, last night when I was preparing, I thought I didn't have enough material for an hour, so I tossed in like 6 new slides about the block layer. And you all like the block layer, so let's see. Those guys. So what is... First, let's set the stage and define what we are talking about here. MMC, the multimedia card, it's been around for quite a while. It was introduced in 1997 by SanDisk, Siemens, and superseding compact flash, which was the previous desired technology for external slot-in files. And compact flash had been around since 1994, where it was used for I think mostly cameras, mostly digital cameras started to use that. So the very first digital cameras, they used compact flash. I guess you have seen those. It's like a big MMC card, big like that. And that didn't really fit the form factor of the new devices coming out, because yeah, phones were not like that, they were more like so you needed something smaller, and they came up with the MMC card. And this was at the same time as you had things like MP3 players and public PDAs. And that's not public display of affection, it's personal digital assistant, that's what it is. Those things were coming out in around 97, so they had to create some kind of storage that could be attached and removed. And the MMC Association started to standardize this protocol 4 years later, or no, the following year, 98. And the competing format in 1998 was memory stick. Have you seen a lot of memory stick lately? No. So they won. And there were some others that never saw the light of day as well. And then 10 years later, this MMC Association of Siemens and the others, they merged into JEDEC. JEDEC is, I don't even know how to expand that acronym, but it's an association for mostly flash memories. And they have been doing a lot of flash memories and this kind of storage techniques, but they also absorb now the MMC specification. And at the time, they thought they would need some managed NAND. They were talking about disks on chip and such things. So he came up with this thing here, the embedded MMC, which is a BGA chip with an MMC inside it, but you just solder it onto exactly the same things that you would otherwise have the slot for the card. And the reason is essentially was convenient, because they had already all the drivers for it, they had the protocol specified, and they wanted to create what was at the time called managed NAND. That is a flash chip which has a bad block arbitration layer, essentially its own microprocessor. So all these cards have a small CPU in them, ARM7 typically, or something like that. And they run their own little software, it's single-threaded, nothing complicated. But there's a very interesting article by Bunny, where he's taking these apart, and you can even change the firmware on them, and everything is awesome hacking if you have lots of time. Which you don't, but if you have, it's very fun to hack these cards. I have to scroll my presenter notes so I don't miss anything. The first specification for embedded MMC for this thing was published in 2011, and at that time, actually the first Android phones were out. So the first set of Android phones and iPhones and so on were not using this technology, which we associate very much with phones these days. They were using NAND flash with its own software layer to manage like bad blocks and block rotation and such things. The typical file system used in the early Android phones was YAFS, yet another flash file system was the name of that thing. But when eMMC appeared around this time, late around 2010, 2011, it took over pretty much everything. In parallel, there's a competing standard. Some people don't really realize it's a competing standard. It's these guys up here. SD cards that you all know from your phones and cameras. It's not owned by the same guys. It's not driven by the same guys. It has a different protocol. It just looks the same. We run it in the same software stack in Linux, but if you go in there and look at the software, you will find there's one file with MMC and there's one file with SD, and you look at the commands and everything is different. It's just superficially similar. So it's like two backends to our subsystem here. I should say I'm not the maintainer of MMC. This is Ulf Hansson, but he's my colleague and he's sitting like in the next room, so I have him at the arm length distance. And sometimes in the office, if I have an MMC question or block layer question, I was like, Ulf, how does that work? So it's very convenient. And I also help him quite a lot with this, and that's why I'm talking about it today. So these guys up there, they are from a totally different legislative body. They have their own protocol specifications and so on. And they have very strictly, actually, electronic differences. What you will notice is, if you use one of these cards, they are internally structured to house the FAT or exFAT file system, the Microsoft file system. Because the blocks that sit exactly where the directory entries of the file system metadata is in FAT and exFAT. Those blocks are much faster to access. And they also never go wrong. So there's special error management for them. So the cards, they have been tailored from beginning to end to house exactly that file system. Whereas in this case, embedded MMC, that's just generic storage. So it will work fine with X4 or ButterFS or something like that that you usually want to use. But if you format an SD card with X4 and or ButterFS, you're going to get strange performance characteristics depending on where blocks are placed on the device, which is not so good. So to make the ultimate SD card hack, we should be able to detect these areas and then handle them differently, and there are some abstractions in the block layer to do that. But we haven't gotten there, we are far away from. But it's interesting hacking if you're interested in working with SD cards. Yeah, the SD cards, they really took off. They were really popular around the 2000s. And they were embedded into a lot of PDAs as well. And the slots to read these cards. And for that reason, they started to create a lot of these guys down here, Wi-Fi cards. You would typically take one of those and slot into your iPack PDA, and then you get wireless. It was expensive, but for a corporate executive, it was of course a must-have. So those had specialized drivers for Windows CE, I think, was on these devices, and mostly we don't have them working today. I would like to fix it, but you know, time. So another interesting thing that Linux supports a little bit so. We have SDIO support in the kernel. We even have dual mode, but because at one time they realized, yeah, if I swap that thing in, then all my storage is gone. So they created a card that was a Wi-Fi and a storage card at the same time. Not a bad idea. Not a very good idea, but I see why they did it. They even had exotic things like that, a little camera that you slot in like that, and it would take images in your iPack. Mostly these wireless cards and cameras and barcode scanners and things that they created there, they are dead now, they are gone. Nobody uses them. Partly because we don't have working drivers for them in Linux and not in Windows, so they were for Windows CE. One thing survived. It's this guy. At the time when the first Android phones and those came out, Atheros especially used SDIO to communicate with the Wi-Fi chip. So they saw, my wireless is something like that thing down there, some kind of wireless SD card. And they put it on a chip like that, and just like in the case of the EMMC, they just soldered that thing into the phone, and then they have wireless over SDIO, over the same IP block that is managing their memory card and everything else. When you make the IP on your chip to manage that card or that card, that is very similar. The state machine and everything, because the electrical interface and the low-level electrical protocol of SD and MMC, they are the same. You can put the same card into an MMC slot or an SD slot. You can even get the adapter for this one, the micro SD that you all have, and get a BGA adapter for that and slot in that chip on top, and it works on any phone, and anything that runs Linux at least. So we have got very high level of compatibility here going on the electrical level. So it was convenient from them from a hardware point of view to solve it in that way. Right. Linux didn't have an MMC stack until 2004, 14 years ago. This was written by Russell King for kernel 269. And that work was inspired by handhelds.org. There were a lot of hackers working on PDAs, Palm Pilots, this kind of types. Maybe you don't even remember them, maybe some of you have nostalgic memories of these things. But a lot of people had their first experience with hacking Linux on embedded with exactly this kind of devices. And that code eventually got cleaned up and merged by Russell. It only supported 2 host controller drivers, that's the hardware that talks to the card. They were the PXA and ARM MMCI, TL180 that we still use today. It was small, lean, mean, and clean. It looks like this. These are all the files of our first MMC stack. It looks like a small thing from some embedded operating system like FreeRTOS or Zephyr or something like that. Just very little. Not so hard to understand, not very big files as you see. It's like, yeah, 30,000 lines of code plus 40, 50, something like that. You can read it in a day and understand how it works. Then something happened. So this is not intelligent design at all. It's just feature creep. Just add in features, 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 features. SD cards got a lot of new commands. MMC cards got a lot of new commands in the specifications, and they started to add them in. SDIO support, as I mentioned, to connect network cards, that had to go in. And then the specification started to add magic partitions, such as boot partitions, and generic partitions, they just call it, and RPMB, replay protected memory block. These things had to be fitted into the MMC stack as well, and then it just grow like this. Not very elegantly, I would say. It was maintained for a long time by, first by Pierre Osman, a Swedish guy, and then by Chris Ball, who was working for the One Laptop Per Child project, and he was doing some Linux maintenance. And then eventually, my colleague Ulf Hansson took it over. So another thing that contributed to this was the speed towards the eMMC especially. They introduced things like double data rate. That is essentially that you read data from the chip on both positive and negative edges of the clock. So one bit out, one bit out, one bit out, one bit out like this when the clock is going. So just ticking out. And then if you have 4 or 8 bits in parallel, you can just multiply by that and you get really high speed. They are working on that for SD cards as well, I think. There are not so very many other intuitive ways to solve it. The problem with the double data rate is, well, you can guess it. You know electronics, clock school. That's what you run into. The nice little pulses here, It works very nice at a certain temperature, and then they start to go like that because it gets warm or get cold. So what you have to do then in the MMC stack is start to retune this clock with after every command, essentially, because the temperature of the device is changing all the time. So the software has to go in, stop sending commands to the card, retune, so the clock pulse and the data pulse are matching like that, and then run a few commands and then retune, and run a few commands and retune. So you can see, it becomes complex. Of course they put it all into software, not hardware. So we get to deal with it. Now something completely different. The MMC cards, SD cards, they are block layer devices, they are block devices. And the problem with block layer devices, or one of the problems with anything with block layer devices, is user experience. And this has been neglected for a long time. And this is sort of an introduction to why I became involved in working with the MMC and SD cards. The user experience with the Linux desktop or the Linux phones. Now we have a lot of Linux phones since everybody's using Android. But the user experience has been sometimes perceived as lacking, like it's shaky or not responsive. You click something, it takes a bit of time. You try to do something, it takes a bit of time. Linux is not ready for consumers, something like that, people just toss out. Why is Mac OS so much better at this? Why is Windows so much better at this? I don't really know, because I haven't really looked at their code. Maybe because they put higher priority on this work just because of the way their architecture is or something like so. Sometimes even those operating systems are not very good at it, and people use these RTOSes in order to get the right responsiveness in a system. They put in VxWorks or Vertex or something like that. But the fundamental problem is the user experience one. And sometimes, and a lot, we have been hunting the wrong thing. We have been hunting real-time patches. For example, people think that their desktop is going to be really nice and fluid and quick and nice transitions if they only get real-time patches into the Linux kernel. That's true for extremely loaded system, if you're like running 15 kernel compiles on your desktop at the same time and your audio is skipping. I agree. Putting up that process to real-time is the right thing to do. Some real-time patches will make sure they don't miss the deadline, and you then don't get audio skip. And audio skip is like, I agree, it's the worst thing ever. It's the worst thing that can happen to you. But there is another thing that will give you audio skip and media skip and video skip, which is much worse. It's when it looks like this, and you hate it when your code looks like that, right? That's horrible. The audio skipping is worse, but the video looking like that is even worse. Or is it now? Audio is the worst. But I just start my Kodi media player on my NAS, and it looks like that. Or on the local hard drive in the worst case, but just because I'm doing a backup at the same time. And people think that, yeah, I have to have my real-time patches. Well, that's not the problem. The problem is not that your process is not getting CPU. You think so, because you are trained to think that the problem is that you're not getting CPU to render your frame or to decode your MPEG blocks, as in this case. Or to decode your MP3 audio. That's not the problem. The problem is the data is not in the memory. It's because the block layer has not brought your data up from the hard drive or from the MMC card or wherever it's stored. That is the real problem. And user experience with this kind of annoying skips in video and audio, that's usually considered a soft real-time task. It's not the end of the world if they fail. It doesn't mean that the car runs off the road or that the heart machine stops beating somebody's heart, but it does mean annoying, so it should very, very rarely happen. It's okay if it happens once a year. Hard real-time, it must never happen. You have guaranteed deadlines. What you want is really soft real-time. And soft real-time is not working because the block layer is not giving you data quick enough. The skips are not caused by file corruption either often. It's just that they can't get the data stream to the decoder in time. this happens on Macintosh. This happens on Windows. It's not even a Linux problem. It happens on all operating systems. And what can we do about that? The work we have been doing in Linaro has been to sponsor and work with Paolo Valente from the University of Modena in Italy. And he has a way to solve exactly this problem. And that's why we're investing in it, because then we can be better than Windows and we can be better than Mac OS and all the free RTOSes, because they don't really have a solution to this. Yeah, we go into the block layer and we introduce a budget fair queuing deadlines. Budget fair queuer scheduler. So what happens in your operating system is you have applications up there, there is your Kodi or something like that, or what media player you're using. GNOME player, I have no idea. It goes through a bunch of file system here. In the BFS layer, there are all the file systems. It might tunnel through the network, but it turns into something called block layer input-output request, or BIOS, and then it goes here into the block layer, and then that talks to the different device drivers. This is where the problem happens, that make your video skip, and will make like blocky output and so on. This block layer has this hardware detached queues, and it takes blocks from above and it tries to prioritize what to read first and next. And there is something in there called the completely fair queuer. This is the default block scheduler. And it's pretty good, I mean, in some sense. But for this kind of interactive tasks, it's not really suited for that. It's done for server tasks where you have to be fair to different I/O from different virtual hosts or different processes running on a server, and you have to share I/O. Typically web servers, typically big financial market backends, these kind of things that people love to make Linux servers for. That's what it's made for. It's not really made for people sitting at the desktop looking at their Kodi media player while the backup is running in the background. They didn't think of that. That's not what it is designed for. That's what the BFQ scheduler is created for. So we wanted to put that in here. With the no-op CFQ deadline, we put BFQ here. And the block layer maintainers, who are nice, and who are my best friends, they said no. That's not going to happen. Okay, why is that not going to happen? Yeah, it's because we're working on this thing over here. Block MQ, multi-queue block scheduler. So you have to put it in there. That's okay, multi-queue, what is that? Everybody knows what multi-queue is? That's good, because I'm going to tell you. Normally the block layer acts like this. You have a number of processes running on your system. They do open, create, read, write, close, and so on. And then everything goes down into this funnel. You see the funnel here? Yeah, funnel. Into the device, where the blocks are that you want to access, read, write, etc. So these are processes and threads. It's essentially tasks, we call them. So we'll go through the VFS and hit the block layer. And then it will pass down to the device. The thing is, it will treat all tasks the same. There are the different block devices. All these things, they will be treated the same in the block layer. There's the old ATA drivers ATA, that's the, I don't remember that acronym, hard disks, you know. And SATA is the latest incarnation of that. That is sitting on top of SCSI actually, so all these things appear as SCSI devices. Also the USB storage appears as SCSI device these days because it's a library, and both ATA and USB storage appear as SCSI devices. There's the old IDE. If you can clean up these drivers to use the AMQ layer, you're very much welcome. The CD-ROM, it's also its own. There are some special drivers in drivers block. There's the managed devices. Then we have our MMC. Memory technology devices, flash devices, also goes in here. And then we have the modern stuff. And these guys on the bottom, this is the reason they are doing block MQ and want to deprecate the old block layer. because these are multi-queue devices. NVMe is a highly managed multi-queue block device, and light NVMe is open channel SSD. So you have, of course, SATA up there, SATA SSD, that you have a lot of you in your computers. If you have a modern laptop, you will have NVMe in it. It has /dev NVMe 0 and so on instead of SDA 0, SDA 1. And then if you're running high-performance servers at Alibaba or Facebook or Google, you want to use this open channel SSD. That's the rough outline of how the storage landscape works. And of course, these guys, us, embedded, MMC, SDIO, we are not important. Not in their world. The fact that we ship 10 million devices with Android with this every day, they just like, yeah, that's nothing, we don't care. So we had to go in, help, improve, and be part of that work. Because, well, the block layer maintainers, they are sitting on this subsystem, and being angry about it is not going to help. What helps is help them to do their thing, so we can do our thing too. That's a special case. Unified flash file system, UFS. It's a kind of SCSI that hides your mobile storage SSD thing behind the SCSI interface instead. That's also nice. So those things. We have to go in and work with everything if we're going to change something, and that's pretty heavy. But yeah, so the problem looks like this. We have a number of CPUs these days. They are putting all the requests in a queue with a big lock on it, and this is the elevator algorithm, as it's called. We're using the CFS, the completely fair scheduler, and we wanted to put in BFQ here, and they said no, and then it accesses the blocks down there. Okay, we can't do this. What was the problem with that? Yeah, it was using fixed weights and so on, and a time-based algorithm. BFQ is not time-based. So what they were using in CFQ is slicing according to these weights, the time that each process queue gets allotted. And then over a quanta, it spins around like this and allots it a certain quanta of the time for scheduling its blocks. That turns out to be, that sounds really nice, right? Like the CPU scheduler works like that. So it sounds like, yeah, it's the best thing. Why do you want to change that? Yeah, it's because this is just a killer for interactivity. It's a good thing when you have an abstract problem. And I don't know what you should compare it to. Like if people are waiting in a line and there are several servants, it seems like, yeah, you just allot it fair, you put as many people in every line and so on. If there's some more important business class passengers here, they have a higher weight, what's the problem? Yeah, it doesn't matter how much weight you give over there if there is something that's super important, interactivity. It should just pass beside the lines, and that's not really working when we test it. So we have to go over to block MQ support. What is that? If we want to put in our new scheduler, we have to put it in block MQ. Here's our old scheduler. Block MQ looks like this. That's a funnel with several pipes on it here. That's my photoshopping here. It's not super good, but it's like a funnel with where information can come out in different places. So they want to rewrite the whole block layer framework from just supporting that over to supporting that. That's what the block layer maintainers want to do. Does it matter for MMC and SD cards? Not at all. We have one queue to the device. It's like an old hard disk, where the heads are spinning at a certain speed. The MMC and SD protocols are specified with one pipe. You can pipeline it, and I'm going to get to that later, but there's essentially one hardware queue. But we have to accept the fact that, yeah, in this world, we are going to have to live with these guys that have several hardware queues. Which is nice for them. There are lots of people working on that. So if we want to future-proof and improve the latency in the system, so we get the more interactive desktop, we have to go over and work on systems like this, or with a scheduler like this. It processes requests, something like that. So we have several CPUs on the top, submitting requests to the block layer in per CPU request queues. You can have several processes on each CPU, of course, but every CPU has a request queue. So it gets first put in here and merged and ordered around in here, and then we get through the block layer here and we put it in the hardware queues. These are the 3 pipes on the funnel. Everybody's following me here. And when they work with that subsystem, let's assume we have this multi-queue problem. We have a SSD, or we have a NVMe, or light NVMe, open channel SSD. What problem do they have in their world? Yeah, they have the problem that they have these 3 pipes and they are unable to fill them because they are so fast. Because they put the request here, they put the request here, they put the request here, this one is already empty, put the request, like, the problem is keeping all these workers satisfied. So their multi-queue scheduler was, or block layer, was entirely oriented in trying to fill up many write pipes as quickly as possible. And they even developed a scheduling algorithm for that that's called Kyber, which is the energy source of lightsabers, I think, but they reused it in this context. So, from Star Wars. Of course, it's geeky. Kyber, what it tries to do is to keep all these queues filled up. First, they had no algorithm at all, but they put in this Kyber scheduler to keep this. Like, if there's halfway here and full here, I should probably increase it there a bit. If it's empty there, put some more requests. So even out here, so it's full in all the pipes at the same time. You get the idea. That's Kyber. But we have this scenario. We have just 1 pipe. We don't need any Kyber for this. Oh, 10 minutes already, my God. We don't need any Kyber to prioritize this. We need BFQ here to prioritize all the requests from all CPUs and classify them so the most important ones go down here fast. And for that we need BFQ, because BFQ will identify interactive processes using heuristics, of course. Not like deterministically, but it will use heuristics. Like, was the process just started? What is the data access pattern? It will look very closely at the data access pattern and see if it reads something that looks like a 1080p frame every 5 milliseconds or something like that. And say, oh, okay, so that's an interactive task, so we have to prioritize that and put those requests through immediately. That's what BFQ does. And it does a bunch of heuristics up here with the processes as well. It's all about identifying and prioritizing interactive loads so that they get low latency, so that your video player does not skip. So we have put in a lot of work into that, and as of kernel 4.16, we have managed to migrate MMC to use MQ. And Paolo has simultaneously, working with us, managed to get BFQ into the kernel. So now it is possible to turn on BFQ, go into sysfs to activate it, which you have to do, and get this exactly thing in place. BFQ there, scheduling the things, getting low latency. And I have run the tests, which are like a lot of scripts that run interactive things like media players and start terminal windows to the left and right, Git operations and kernel compiles and such things. And it delivers. It's wonderful. It really is a big win for all Android devices, just that Google haven't realized it yet. Maybe I'm smarter than them, maybe I'm not. We'll see. Probably not. They probably have some good reason why they haven't just ran all over to it. Maybe they want it to mature or something. But I think it's the best thing, so you should definitely use it if you can. What else have we been done? Yeah, I mentioned this, that we have only one submit queue for MMC. So everything goes into one queue. How do you possibly improve that? You do exactly what the CPU does. You do pipelining. So I start one command, like read data blocks, and then before that has finished, I send now the next command while I'm still streaming up data from the card. Say read another block, and then just keep submitting things and put it up in the pipeline. So whenever the card is idle, it just takes a new command of its internal queue. So there's this queue is inside the kernel, inside the card, the MMC card, and it just picks and picks and picks. It's for eMMC, MMC only, not SD cards. No, they will come up with something similar, I bet, but it's going to take them some time. This we also fixed. Adrian Hunter from Intel finalized this for kernel v4.16. I insisted that he delete also the he implemented both the multi-queue block layer for MMC and command queuing. And it performs really well on SDIO hosts. And I insisted that don't keep the old block layer around, delete it. And he was a bit grumpy about it, and we were fighting and saying nasty things, and then he deleted it. And it just works. We will never go back to the old block layer, I'm assured. Multi-queue, command queuing, VFQ. All that we have in place. And there are things that I want to fix. Like we have this problem. I can usually make a backup of a SDA, like SCSI disk like that, just DD from the disk into a file, and I have an image. It doesn't work with MMC cards. You will get a backup of the primary partition, but all the boot partitions and generic partitions and what they have invented, they're not part. Because when they invented these things over here, boot partitions, RPMB, yeah, they implemented them as their own block devices, and they shouldn't have. So now I have to fix it, if I have time. I fixed this one, RPMB, this one. I fixed this. I converted that to a character device. Is this? This is not yet a character device. You see, it has a block device, but I've converted it now to a character device. Last v4.14, I think. So it's all fixed now. Nothing broke. It's fine. So there's some such things we need to clean up. This is all too complex. So I need to do that. I need to take care of the partitions. I have some ideas about it. I need to get rid of the dual mode card support, which is storage and SDIO in the same card. Split the MMC and SD block access from SDIO access, so we have either SDIO or blocks. And then I can get rid of this shit, this block, big MMC lock, which is like the big kernel lock. It's not really good at all. It's just very complex syntactically. It's almost never used. You just enter it and enter it and enter it and leave it and leave it. There's no like exclusivity coming from it. But we need to get rid of it because it's horrible to deal with. So yeah, that semaphore is just I don't understand it. If Ulf was here, he could explain it to you. Alright, we have a few seconds for questions about MMC, MMC, SD, SDIO, and the block layer. Did anybody understand anything? No. Okay, good, good. Gentleman over there.
So you say that the problem with interactivity is located in the two parallel schedulers, yeah? Either the data should be processed by the scheduler that cannot be touched because of your colleagues permit, yeah? So you found the bottleneck, yeah?
Yeah.
And suggested you to fix it in the multiple
multi-queue.
Yeah. And so this is a kind of the dialogue, yeah, between colleagues and you. You have a kind of management who decides whether this is a reasonable idea to change or not, yeah? So you cannot just stand for your idea that it's really valuable and this makes the world better, or it was just a management decision, we should not break things.
No, it wouldn't even break anything to introduce BFQ on the old block layer.
So
there are patches for it, they work.
Okay, yes.
The problem is entirely maintenance point of view for the maintainers. So it's time, like Jens, who is the main Jens and Tejan Ho, they are the main maintainers, and they get a lot of help from Christoph Helvig to maintain the block layer. They now have the old block layer and the old block scheduler, and they have MQ, and they have to maintain all this code. If something is wrong there, there's a high risk they have to go over there and fix it, and if something is wrong there, there's a high risk they have. It's just too much work for them. They will have to recruit new maintainers for maintaining just the old block layer and focus their efforts on the multi-queue block layer, which is where they do most of their work, since they work for enterprise companies like Facebook and Google and so on. So they are not really interested in that old code because none of their devices that are important for their production systems use it anymore. So they just throw out their hands and say, we can't maintain this mess anymore. If you're going to add another scheduler policy and we have to review and merge patches, add it over here in the multi-queue scheduler, which we are actively working on. And first Paolo said, but there are not even any interfaces for a scheduler. You can't even add that Kyber thing you're talking about. Oh, okay, we fix, and they hack, and they fix. So we integrated, and there were lots of other problems, but now it's actually working.
But what you showed us the problems with interactivity can happen on the desktop, which are not often use SD.
No.
So your presentation is about SD and MMC, yeah? But mostly video and audio files stored on hard drive, yeah?
Yeah,
Does it go by the same queue?
Yeah. Desktop has exactly the same problem, especially if they have a multi-queue device like an old hard drive or a single channel SSD. They, like a SATA drive, for example, you will have exactly this problem. It's just that SATA drives are so quick, so you usually don't notice it. But the exact same problem appears in desktops. And you would think that these guys would be interested in solving it. They are not. They are working on servers. Servers don't have this problem. They don't have interactivity problems. Unless they are working with streaming and something, and then they usually have other problems with network latency that are more acute. They are more interested in solving that. So that's the whole thing. They are not really, that's not the focus area of their interest. They want to solve it. Of course, they think it's an interesting technical problem. But if we come running and say, like, it's the most important problem in the world, they are like, yeah, that's the most important problem in the world. You know, it's just a question about what you have in mind in front of your face. Like, they want to, yeah, sure, you can have it, but it has to be in this place over here, and that's how it works. So we are working with them we have implemented it now in the multi-queue layer, and we are working actively to deprecate the old block layer so they can just maintain that body of code. And yeah, it's a bit of compromise. It's more like a Cold War or something. You have to talk to the different diplomats.
Yeah, you may also still return it to the situation if you have already patched it, which was verified.
Pardon?
I said that you may return to this question with your management if you have already patched for the first scheduler, so that they will review one day.
Yeah, it's a question about maintenance burden for them, because it's going to end up as money of work hours for them, and they don't have so much hobbyist time. They're working full time already with this. They just like, no, not more, thanks. Just help us to get rid of the old
Linux, it's an open source, so community also can support maintaining.
Yeah, they could recruit more block maintainers. There are just very few people that want to work with the block layer. They don't have very many candidates. They only have these few people. Like, if it's because they are not letting people in, or if it is because, well, people are not coming to them, social question, sociological, I guess. It's because of, yeah, we haven't educated enough computer science people who are interested in open source. Sorry. Please get involved, all of you. We need it. There are more questions. Awesome. Oh, that's Pavel. Thank you.
Sorry about that question. Can I help the scheduler by marking task as background? When I am running backup, I would be willing to say, hey, this is a backup.
Yeah, there is something called ionize. There's a command already called ionize. So in the old block layer here, there is a tool to set these weights, and it's called ionize. And you can set it into real time or background and so on. The CFQ scheduler that we use today for single queue will take it into account and adjust the weights accordingly. Unfortunately, the media player still skips.
Yes.
Because it's not working as you expected. It will give these weights to the different things. So eventually what they will get is the right amount of CPU time according to these weights. But it doesn't say that it will do something useful with those CPU cycles. So it gets a certain allotment of wall clock time. But that's not what you want. What you want is a number of gigabytes throughput to the device, and that's how BFQ is done. It's, instead of measuring time, it's measuring throughput in kilobytes, megabytes per second.
Okay, so what I actually would like on my spinning grass, if I have interactive task and it needs I/O, I would like the disk to wait for him, like 10 milliseconds for next I/O. I keep it idle so that it doesn't move the head somewhere else. Is that possible?
That's exactly what BFQ is doing.
Okay, I should try it.
Try it out. It will work, I hope. You have to turn on MQ in the SCSI layer and say that let my SCSI layer use MQ, and then you have to go into sysfs and say that the block layer scheduler you want to use is BFQ, and it will do exactly that. So 2 steps, but then you're home, then it's actually working.
Thank you.
Thanks for the question, Pavel. Excellent question. Any more? I think I'm out of time, right?
Yeah, you have some time. Any questions?
No. Okay, you understand it all now. Thanks.